Hi everyone, Mrs. Below here. In this video I'm going to be going over noble gas notation, how to identify an element given the electron configuration, and ion electron configurations. So first thing, the noble gas notation is just like a regular electron configuration, but it's like a shortcut or a shorthand version. So instead of me writing out 1s2, 2s2, 2p6, instead I can replace that with neon and then write the rest. So the noble gases on your periodic table are these elements right here. So you want to label those on your periodic table. These are the noble gases. Okay. And so we can use those as a shortcut so we don't have to write something super long like this. So the hint is to look for the noble gas that comes before the element you want to write the notation for. So let's do an example here with calcium, and we're going to write the noble gas notation for that. So I got to first find calcium, which is right here. And I'm going to look for the noble gas that comes before it. So again, I'm just going to highlight them. These are the noble gases. So if I go backwards, this is number 20, number 19. If I go here to 18, that's argon, and that is a noble gas. So I'm going to write argon in brackets here. So instead of me writing 1s2, 2s2, 2p6, 3s2, 3p6, I just wrote argon. So all of this is being represented by argon. And then I just continue writing from there until I get to the element I want, which in this case is calcium. So then I would continue my notation with 4s2. 4s2. And this would be my answer. Let's do another example. For this one, instead of bromine, I'm going to do something that goes through the F block. I'm going to go ahead and do iridium, which is IR. Okay. All right. So again, we're going to look for the noble gas that comes before iridium. Just going to cross this off. Okay. So here are the noble gases. Okay. So iridium is here. So I'm going to look for the one that comes before it. So this is 77, 76, 75. If I keep going backwards, we would have xenon, which is number 54. So I'd write Xe, which is xenon. So again, instead of me writing 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, 5p6, I just wrote xenon. So all of this is included as part of xenon. And then I'm going to continue from there. So I have 6s2. And then most of you would probably want to continue here to 5D. But remember, we have right here, it says 57 through 70, which are these elements here. So I kind of like have to take like a little detour, so to speak. Okay. So instead of going to 5D, I'm actually going to go 4F. And then there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 boxes. And then I can continue here at 5D. So when I was reading, I read here, and then I read here, and now I'm going back up to here. So 5D, 1, 2, 3, 4, 5, 6, 7. 5D, 7. And that is noble gas notation. And this is more of like what you would see on a test, is something that does go through the F block for the noble gas notation. Next is identifying the elements. So this part is really easy. All you have to do is look at the last thing written for that element. So for example, if this electron configuration ends in 4p1, well, I would just go to like 4p and I would count 1, which is Ga, which is gallium. So for example, this one, I have 3D2. So I would find the D block 3 and I would count over 1, 2. That is titanium. This one ends in 6p2. So 6p, and then I would count 1, 2. Pb, which is lead. This one ends in 2p3. So 2p, and then I would count 3, 1, 2, 3. That is nitrogen. And then lastly, I have 3d6. So 3d, 1, 2, 3, 4, 5, 6. That is iron, which is Fe. All right, lastly is ion-electron configurations. So remember that ions are things that have a charge. So that means the number of protons and electrons is not the same. And this can happen when an element or atom gains or loses an electron. And when that happens, then we have a charge. So if you are losing, remember, electrons have a negative charge. So if you lose electrons, you would become more positive, so you would have a positive charge. If you gain electrons, you're gaining negativity, you would have a negative charge because you're gaining electrons. So when it comes to an electron configuration for that, you would want to start by looking at the regular electron configuration for that element. So here's the regular electron configuration for fluorine. It is, just get my ruler. Cross out. So fluorine is 1s2, 2s2, 2p5. So that's what fluorine normally is. Now fluorine, on your periodic table, if you look, the row up here, it has a -1 sign. So fluorine has a charge of -1. Well, if you have that, that means it's negative. So this means that you gained 1 electron. And so instead of being 1s2, 2s2, 2p5, because you gained that 1 electron, this would become a 6, because these numbers that we've been writing represent the number of electrons. And it would be a 6 because we gained an electron because we had a charge of -1. All right, so this is a typo, so please fix this. This should be a 2, actually. Okay. So again, here is the normal electron configuration for calcium. Okay. And so if the normal electron configuration is 1s2, 2s2, 2p6, 3s2, 3p6, 4s1, and we have a charge of +2, we have a positive charge. That means we lost negativity, so that means we lost electrons, and in this case 2 electrons, because the charge is -2. or plus 2, excuse me. And that's supposed to be a 2. So if we lost 2 electrons, instead of adding to this configuration, you could actually just erase this, and this would be the correct answer. However, most students, they'll just go ahead and write this, and then they'll cross it off to show that we lost 2 electrons. So let's do some practice problems. Okay. All right, so let's write the ion electron configuration for sodium that has a charge of +1. So you'd start by writing the regular electron configuration for sodium. So we have 1s2, so 1s2, 2s2, 2p, 1, 2, 3, 4, 5, 6, 2p6, and then 3s, and then sodium is right here, so we would have a 1. Now again, because this is a charge of +1, that's positive. That means that we lost electrons because we lost negativity. So we lost 1 electron. To show me losing 1 electron, this is 1 electron represented here. Instead of just doing like this or crossing that off, it'd be like you can't just write 3s. That's weird. You can either get rid of the whole thing, okay, and this would be your correct answer, or you could just cross off the 3s, and that would be correct as well. All right, let's do another example. So we have sulfur that has a charge of -2. So again, I would write my regular electron configuration first. So 1s2, 2s2, 2p, 1, 2, 3, 4, 5, 6, 2p6, 3s2, 3p, 1, 2, 3, 4, and then that would be 3p4 because we're going only to sulfur. And then this has a charge of -2, which means we gained electrons. In this case, we gained 2 electrons because electrons are negative. So if I gained 2 electrons, instead of this being a 4, I would add 2 to it. So 4 plus 2 would be 6. So something that you should have noticed with these electron configurations. This ends in P6 now. This ends in P6 now. This is ending in P6, and this is ending in P6. So no matter what the ion is, it's going to end in P6, and there is a reason for that. So they all, and this is for ions, end in P6. And if you notice, all of those, if you were looking at P and you counted 6, those are all noble gases. And noble gases are known for being not reactive, but in fact very stable. So these elements are gaining and losing electrons in order to become like the noble gases, which are very stable and unreactive.